Okay, thank you very much, Mark, and thank you all for joining the e-seminar today, Getting Ahead with Lightning Strike Simulation. As Mark mentioned, before I start the slides here, this is really focused more on the practical usage of the software. And, we chose the topic of lightning strike simulation after some feedback from you guys, our customers, from last fall, where we had kind of an E3 simulation webinar and kind of overview. But lots of the feedback was, show us how to do it, show us, how you define, for instance, a component A waveform versus a Heidler waveform, and, how do we actually define the sources? How do we obtain outputs for a lightning strike or E3 type of simulation? So that gave us the motivation to do this Getting Ahead with webinar today. So just to give you, let's see, advance the slides here. There we go. So yes, it is about 45 minutes, and you might look at this and say, wow, that's a lot, but we're gonna make it happen here. So I'll talk about kind of the motivation and introduction for lightning strike simulation and EMC simulation in general, and then we'll talk about the different modeling approaches, because lightning strike is a fascinating phenomena. It's a multi-physics phenomena. It's multi-scale, so there's lots of challenges when you want to try and simulate this, and there's different approaches. You have the electrostatics aspects. You have maybe quasi-static simulation or full-wave simulations, or multi-physics coupled EM, thermal, even structural simulations. So how can we approach this and, kind of differentiate between direct and indirect effects of lightning strike as well? So that'll just be kind of an introduction, but then I'll spend the vast majority of the time doing an actual demo of an indirect effect simulation, basically the return stroke analysis of lightning strike. And we'll basically build up a model from scratch. This will show you things like using the project templates, how to define a source or import your own source. What are the boundary conditions? Does it matter whether I have, a certain port location or a certain length of the channel that I'm modeling? And then we'll spend a lot of time looking at the different outputs that you can have, discussing materials modeling and so forth. So hopefully this gives you more insight and more tips and tricks, more or less, in terms of what you can do with CSD Studio Suite for lightning strike simulation, and in this case, focusing on the indirect effects analysis. So then I'll conclude, provide some further information, and we'll have a Q&A. So why EMC simulation, right? Why do we even want to simulate EMC phenomena? If you're involved in EMC, you know this very well, that as time goes on, the cost of a change, if you discover a problem or you don't pass, is going to be astronomically higher than if you considered that early on in the design process. So ideally, EMC should be considered upfront, early on in the design process. Unfortunately, it falls, to the bottom of the list in some cases, when you have other requirements such as thermal, structural performance, and things like this. But basically, this can result in delayed time to market if you have to do respins of your electronics, or you have to, find solutions and mitigation of these EMI problems. So simulation can help in this, and it can not only be used for kind of, early on pre-compliance design, if you will, but also troubleshooting and investigations when you discover that you do have problems. And so for lightning strike specifically, and I really love this image, so I decided to show that here. Of course, lightning strike is a very complex phenomena, and we, have electrostatics to consider, as well as the return stroke phase and multi-physics aspects, all of this, like I said. So, especially in aerospace and defense, I just wanted to list some of the industry standards here for EMC and E3 applications. So you might be familiar with RTC IDEO 160, revision G, section 22 for lightning-induced transient susceptibility. And then there's also, of course, military standard, 461G, CS117, as well as 464A, requirements for systems and system-level susceptibility versus electronic equipment and subsystems. And then you have requirements from the FAA and SAE, ARP, et cetera. And so there's so many standards, there's so many test setups, waveforms, multi-burst scenario, multi-stroke, lightning protection system levels, all these things to consider. And so one might look at this and feel a bit, that it's a bit daunting to consider trying to simulate lightning strike. How could you possibly do something like this? So I want to give you an introduction into what's possible, and, also give you some ideas of how this can really be useful, especially for trying to investigate and mitigate problems early on. So, don't think of it also as that you have to set up a simulation model that specifically mimics one of these standards that you have to deal with in order to, pass compliance. But simulation can be used as an additional tool, basically, in your design process and throughout the design process. So first, thinking about the electrostatics, consider you have an aircraft, of course, flying through the air here, and we have a thunderstorm, thunderclouds building up here with positive and negative charges, and you've got some negative downward cloud to ground lightning event here. So you have a high electrostatic field that's built up between a negative charge in the cloud and positive charge on the ground. You have these stepped leaders that are propagating outward. As the aircraft approaches, the stepped leader may come to the aircraft extremities, and we know that this will most likely happen at geometries with a small curvature radius, so that these sharper objects, right? And, eventually you have this return stroke current that's going to flow from the positive to negative charge once this aircraft basically completes this lightning channel, right? So the first thing to think about here is electrostatics and lightning attachment. And we can use electrostatic solvers to do kind of attachment zoning analysis. Like I said, of course, we know very well that lightning is attracted to geometries with small curvature radius. And so you might want to look at a certain geometry and see if I have a particular boundary value problem with, electrostatic field and a potential gradient in a certain direction, what do these field enhancements look like on a particular geometry, like an aircraft? So I just want to point this out, that this is, one of the types of analyses that you can start with when you're thinking about lightning strike simulation. My colleague Marco Kunz had a nice paper last year in this ICOLSA conference. So if you're interested in more details about the electrostatics analysis, you can look into this reference here, this paper. But also we've had some demonstration of this in previous webinars as well. So know that lightning attachment and zoning is one place you can start for the electrostatics. Now, of course, if we go back to our diagram here, then we're going to have the return stroke that flows, in this case, from the ground, these positive charges, to the negative in the cloud. And, of course, you can also have cloud-to-cloud lightning, and these things can happen as your aircraft is flying up in the air. When we think about the actual lightning attachment and that return stroke phase, of course, the first thing to think about is the damage and, the actual attachment of that that lightning strike to the aircraft. And this can be catastrophic, of course. So, of course, you could have things like fuel tank explosions, which happened in 1967 due to a lightning event, electrical failures of the critical avionics inside the aircraft, and degradation of the structure, especially with composites used so much in aircraft today. So thinking about this sort of direct effects, sort of multi-physics challenge, simulation can also be of interest here. So just going on to the next slide here, especially, like I said, with composite materials, this is just showing a small section on the inside of a Boeing 787 Dreamliner, and you can see here. So disassembled carbon fiber fuselage section. So you might want to home in on a specific section, not necessarily the whole aircraft, but just a small section of that to see when this lightning attaches and I have this extremely high current flowing onto my structure, what's going to happen. And you can look at this stringer analysis, which we've also shown in some previous webinars. As you can see here, you might do a detailed section with this skin stringer panel, including the very detailed stack up of these carbon fiber composite plies, with different fiber directions, different thicknesses, and also, of course, the electrical conductivity, anisotropic conductivity is a really important thing to consider here in terms of the behavior of the currents in the fields. And so we can use a low-frequency kind of magneto-quasi-static approach for something like this, use a LF transient solver. Of course, you can have statics, quasi-static simulations, and full-wave simulations. And so if you're really homing in on just a small area and, not looking at you know, a model that's becoming comparable to a wavelength, then you can use these quasi-static approximations and magneto-quasi-statics in this case. So we can, you know, basically inject a current here. This is at the top here where you see the little lightning symbol in the cylinder. So this is a current source onto the structure. And from this transient quasi-static simulation, we can obtain ohmic losses and basically obtain a heat flux distribution. So here we can see a plot on the different layers, first layer, second layer, third, and so forth, and also the stringer showing these losses. That flow is described in a lot more detail in David's webinar just this past fall, so here's a link to that if you're interested in seeing more about that. But I just want to bring it up as part of the overall discussion of what could be done. Of course, this is also getting towards the multi-physics aspects. And so from 2014 Simulia Community Conference, there was this very nice paper about simulating damage, actually considering the structural analysis as well. So not only from the thermal, and obviously you have this extremely high temperature, but also you have a shock wave to consider, and how does this all affect the damage that you might actually get on the structure. So those are just some references for that. And I want to come back to this diagram again. So of course, you have the electrostatics aspects, the magneto-quasi-statics, and maybe multi-physics aspects. And then you might just be concerned about the indirect effects or the return stroke phase of the lightning event, which is what I'm going to focus on primarily today. So of course, you have this high current flowing through the structure, and you're going to have magnetic fields that result from this, very high magnetic fields. And those fields can couple into cables inside. And especially in the composite aircraft, of course, this is much more susceptible compared to just a pure metal aircraft. You know, these cables, in combination with the composite, you could actually have, you know, the cables affecting the Q inside this aircraft cavity. And of course, the level of current that will flow on these cables is going to change drastically when you have composite materials compared to metallic materials. So all these things need to be considered. Just thinking about that transient current analysis here, we can model, of course, in CST, a transient waveform, which you can see at the top right is just the typical component A, double exponential waveform. And, you know, if we take a Fourier transformation of this waveform, we can see the spectrum there. And it's a relatively low frequency phenomena, of course. Most of the energy here is below, you know, 10, 30 megahertz or so. So what that means is that wavelengths are relatively large. And if you've got a structure you're trying to model, you can cover large distances with relatively coarse meshes because we don't have to go as dense with the mesh in order to resolve really high frequency or small wavelengths, right? And so this makes aircraft level simulations actually possible, and especially with HPC and GPU computing and so forth, we can do quite a bit for this low frequency transient analysis, including the full wave simulation. So here you can see an example that we'll look at towards the end of the webinar of this aircraft, in which we've you know, basically defined an attachment at the front here with a current port excitation. And then we have an exit wire towards the back of the tail there. And we're looking at here, you know, several cross sections of the resulting magnetic field from this high transient current that's flowing through this lightning channel that the aircraft is a part of. So that's just a kind of broad introduction to all the different approaches we can take in terms of modeling. And now I'm just going to go right into a demonstration of this. So we're going to start from scratch, look at this indirect effect simulation, and see what's possible there. Okay, so let me open this up here. So yeah, I hope this meets your expectations with the getting ahead with. Basically, I'm really going to try to show you guys how easy it is to get started with this, things that we've done in the interface to make this easier, and also maybe show you some new things that you maybe weren't aware of in terms of the modeling capabilities. So yeah, we're going to go ahead and get started with a new project template here. And you can see, of course, the different application areas that we support with CST Studio Suite, including EMC and EMI. And lightning strike falls underneath conducted susceptibility type of simulation. So I can choose conducted susceptibility. I select lightning here. You can see also ESD or VCI are there. And for lightning strike, conductive susceptibility, our time domain solver, especially with the TLM method, is very well suited for this type of problem. The project templates will recommend different solvers for you for a particular application, so this is already helping you get started if you're new to the software and new to the tool. So I'll use the time domain solver here. We can set up our dimensions that we want to work with for the problem, the frequency, units, and time units in microseconds. And for now, I'm just going to leave this blank, but you could define, a specific frequency range here and which field monitors you want to observe as outputs. But I'm going to leave it blank for now, and you'll see why as I demonstrate this. So you can give this template a name, call it live demo here, and go ahead and click finish. So this will open up our Microwave Studio. And you can see, of course, you have the 3D GUI here, our navigation tree, parameter list, and home ribbon at the top here. So, of course, when you go to modeling here, we can import 3D CAD, which is most often what you might want to do if you're doing an aircraft level simulation, for instance. And so you can see the different formats that are supported here. But we can also do very simple studies, and that's what I'm actually going to do here today, is basically construct a cylinder representative of a fuselage, and then we'll build up the complexity as we go with that. But the first thing I want to point out is we've just opened up a lightning strike project template, right? And so you can see down here in the parameter list, we have a T-total, T-rise, T-fall, and so forth. And this is actually the parameters of our double exponential excitation waveform. So here under excitation signals on the left, you'll see this double exponential that we'll use as a current excitation. Okay, and you can see, of course, if I adjust parameters such as T-total, I can update this, and we can see how that changes and updates the waveform. Parameterization is a really nice thing to have, especially when you want to do these kind of what-if scenarios and so forth. So for this demo, I'm actually going to just look at the first 15 microseconds. Okay, so we're going to update our waveform to be just the 15 microseconds. And the other thing I talked about before was I left the frequency range blank here. If I go over to my simulation ribbon and choose frequency, we can see that this has also been parameterized to set the max frequency according to the rise time of this double exponential. Okay, so there's some VBA command here which is just getting the frequency unit, but basically what that's doing is setting our max frequency according to the rise time. Something you may not know is I can just copy that there. And on the home ribbon here, I have a built-in calculator. So if I just enter that expression into here that I copied, paste it, you can see, okay, this is 0.645 megahertz, so 645 kilohertz, and that's based on this T-rise of 1.55 microseconds. Okay, so just some tips and tricks about things in the interface there. So, yeah, basically I'm going to actually modify that frequency though, and then we're going to simulate, up to 10 megahertz in this case, just as an example. And along with this parameterization of the double exponential waveform, you might wonder, okay, that's nice, I have this built-in double exponential, but I want to define my own waveform, right? So how can I do this? Right here in excitation signals, you have the default TLM that's always there when you use the TLM solver, the impulse, and also the double exponential. If you right-click here, the first thing is you notice you can define a new excitation signal. So this could be of the basic signal types that we have, but you can also import an ASCII table or a text file. Okay, so I can choose that option here, and if I have my text file ready to go here, I'll just open that so you can see what it is. Basically, it's on the x-axis we're going to have time in seconds, and then of course the y-axis the amplitude. And so I can use this text file, call this lightning signal, and I can go ahead and import that one here. So it's pretty easy to define your own excitation, whether that's the component A waveform or some other variation, or whatever it is you want to do. So that's the whole point. Now, also note that I just called that lightning signal. I can right-click on that and I can add this to my signal library. So there are lots of libraries built into CST, so I can go ahead and save this as, lightning signal, export it. Then when I go to my excitation signals again in this project or any other project in the future, I can, of course, load from the signal library. And there it is, my lightning signal. You can see I had another one the other day on 319. So that's very easy. You can also reuse these signal waveforms in Design Studio as well on the schematic. Okay, so we're going to go ahead and now build up our structure. And I'm just going to start with a simple cylinder here. So going to the modeling ribbon, I can go ahead and click here to create a cylinder, or I can, of course, enter the dialog box and we can define it this way. So I want it actually to be oriented along the X direction. This is going to have about a 3 meter radius. Remember, we're in units of meters here, which you can always see at the bottom right. And I'm going to parameterize the length in the X direction. This is always good practice to parameterize your models, either whether you create them from scratch or import them and make some modifications. And so if I try to preview that, okay, it doesn't know what L is yet, but we'll make this about 50 meter length. And this will be length of cylinder. So we can get a preview of that here. And of course I can choose what material that is. So I could make this PEC, or I can load from the material library. And of course one thing that's available there is aluminum. So I'll just go ahead and choose aluminum to start with. Okay. So there we have a cylinder. And basically we want to simulate this return stroke analysis where we're going to have an entry wire and an exit wire. Okay, so how do we define these wires? You can use curves and you can create wires from curves very easily. So I'm going to go ahead and choose a line curve here. And while you're in these picking modes and drawing of the curves, you can always still rotate the model around. So I know a lot of people kind of stumble with this. So you can still zoom in and out with the cursor. You can still rotate. And I can also use picks in defining this line. So I'm going to go ahead and pick that endpoint there where I want this lightning channel entry to attach to. And then I can just come up here with the curve. You can see that when I use a pick, it's going to enter these parameters in here. So, I can reuse those, or I can enter, this is going to be minus L over 2, because I want it to stay attached when I change the length. And then Y2, I'm also going to define another parameter. So this location where I started plus LW, which will be length of the wire. And I'm just going to start with about 25 meters for this length. We'll come back to that, the decision on that length there. So length of channel wire. Okay. And so I've got my curve. I'm going to do the same exact thing on the other side here. Choose a line, make a pick with P. Come down here. Okay, it was pretty close, but not quite. This will be minus L over 2 and YP2 minus LW. Oh, no, I made a mistake. This is plus L over 2. So preview is always helpful so you don't, mess something up, which even the simulation support experts do every now and then, as you can see. Okay, now I've got these lines. Here I've got in my modeling ribbon, wire from curve. And I just select that, and then I choose which curve I want to transform into a wire. So I double click it. I'm just going to choose this as PEC. This is called entry. Same thing down here. Wire from curve. Double click it, enter, exit. Okay. Good, now we have an entry and exit wire, and we need a source defined on this wire. So again, we're doing this return stroke analysis where we're basically going to use these wires as modeling those, basically that channel. And of course, you might want to consider a case where, the lightning comes in and this channel is formed with a in a different direction. It's not perfectly straight down. It has some curvature to it, and there's always the question of where do I actually place the source, and how do I take this into account with the boundary conditions, and how much space do I add around this so that I get good results, and all of these types of questions. So these are all somewhat related, and I'm going to demonstrate this to you now. When I go to my simulation ribbon here, we chose the frequency, we have the background properties, and I can choose a certain amount of space to extend this bounding box around my structure. Okay, so the background is just going to be type normal, which means this is modeled as vacuum or air. And I can apply a certain distance in X, Y, and Z directions. So I'm just going to use the length of the structure and choose to be half of that. So L over 2 in negative X, negative Y, or sorry, in negative and positive X. In the Y direction, I'm going to add 0 distance because I want those wires to attach to the boundary. Okay, and then same thing here. So that creates this bounding box here. Now the reason we're going to have these wires attach, right, is because basically you're injecting a current on the wire that's going to flow through our cylinder or aircraft, what have you, and exit to the boundary. Now you'd think that we need a conducting electric boundary condition in order to complete that current loop. Of course, that may create artificial box resonances, and if you're trying to model the scenario of the aircraft up in the air, you really want open boundary conditions so that any fields that reach those boundaries are going to be absorbed or effectively extended as if there's open space there, right? So when I go to my boundary conditions, that is what's set up as a default with the lightning strike template is open boundaries. And you can see that that wire will just come up directly to here, okay? Now, in order to define the excitation, all we have to do in the TLM solver with this lightning strike workflow is select the wire, so I double click on it, and I choose a discrete port. And what that's going to do is allow me to place a discrete port at either end of this wire here, okay? So a discrete port models a current source in this case. I can give this a label, a current of 1 amp, which will be multiplied by my excitation signal, which has obviously a 200 kiloamp amplitude. And I can choose which end here. So basically this effectively models a current, coming down from open space, conducting along this wire, flowing through our structure, conducting down the exit wire, and then it's absorbed. So basically these open boundaries, when they're touching the wires, you can think of as effectively extruding the length of those wires so that we're looking at the effects, of these magnetic fields around our structure. Now you say, okay, you chose 25 for the length here, right, of the wires. So if I choose 5, then I'll be, closer, and I'll have a smaller computation to solve. But maybe I'm then concerned about the coupling of the boundary to the structure or the port. And if I make this really long to avoid that, then I'm okay. But then I'm making my simulation much, much larger than it needs to be. So what's the happy medium, and what's the best practice for that? And people are always interested in this question. Basically, as a good rule of thumb, think about adding a certain amount of space that's comparable to the structure you're considering. And, we've done studies of this, but basically what you want to model here is you've got a current source here at the end of the wire, and you have conducted currents down, and you're going to have a resulting magnetic field from that. So as long as this is, not directly above the structure, then you don't have to worry too much about these effects, right? So a good compromise is something like, an amount of space comparable to the structure. So this is giving you sufficient space away from the boundaries and the port and so forth in order to basically look at the effects of those magnetic fields to the structure, the fields inside, the coupling to the cables, and so forth. Okay. Good. So we've defined our port. We have our conducting wires. We've got our excitation set up. And basically now we need some outputs. So if I excite this, if I drive this simulation now, we can run it, but I'm not going to get any outputs that I care about. So I want to define a current monitor around this cylinder. We have current monitors, we have field probes, field monitors. So what do each of these mean, and what can we get from those? Basically, a current monitor is going to integrate the magnetic field along its path so that we can get the current enclosed, basically Ampere's law. Okay, so in order to place that current monitor here, I can draw a curve, a circle, and I can always draw those curves on this working plane here, but my working plane isn't quite aligned to the structure the way I want, and this is where the local working coordinate system comes in. So I can activate from modeling this working coordinate system, and now I'm still oriented with u along x, v along y, and so forth, but you can rotate this working coordinate system. You can move it and rotate it here, but I also use the shortcuts Shift U, Shift V, Shift W, just to change that around very quickly. So Shift V, you can see, just rotates that by 90 degrees, and Shift U and Shift W, as I said. So now that I've got this oriented this way, I create a circle. I can double-click the center point, extend my cursor to set the radius, and we don't need to make it this large, maybe just encompassing our cylinder of radius 3. And once I have this curve, I can go to simulation, choose current monitor, and then I'm prompted to select the current path curve, which will be this one here. Okay. So you can invert the orientation, which will just determine, the sign depending on which way the current is flowing. And there we have it. So I might want to also look at the field inside the cylinder and the fields outside the cylinder to do a comparison. How much shielding effectiveness do I have with a particular structure? So right now this is solid, but I can select that cylinder. Under modeling, find shape tools, shell solid or thicken sheet. If you have a sheet, you can thicken. If you have a solid, you can shell it out. And I'm just going to use 0 thickness here for this conductor for now. Okay. So if I use my cutting plane now up here, which you can see Shift C is an easy way to toggle that back and forth, we can see that we've hollowed out that cylinder. So now that I've done this, I can define a probe, a field probe, inside and outside the structure. So here under simulation and monitors, we find the field probes. It's also, of course, in the navigation tree here. And I'm interested in looking at the H field here. And we can define this at 0, 0, 0, which is right in the middle there. You can apply this. Maybe also do one at 0, 0, 5 in the Z direction here. You can apply, and also 0, 0, 10. So we expect to see a lower amplitude of the magnetic field farther away, and we can actually take a look at that once I run this simulation. Okay. Now, one last thing is the field monitors. Field monitors allow us to visualize either on a 2D plane or 3D volumetric visualization of the fields or the currents and so forth. So you can define, for instance, an H field and surface current monitor. And these can be defined in terms of a specific frequency or as a function of time. Now, especially for time domain simulations and transient phenomena that you're simulating, these time animation monitors can be extremely insightful. So we'll take a look at that here. So I can define an end time, a step width for this. We're going to use 0.1 microsecond step width, basically to 15 microseconds there. Can apply that here. Okay, so there we have our field monitors, our field probes. I have a current monitor, and we can go on with our simulation. Now, again, I'm using the TLM solver here. The accuracy is set to no check because it's just set to run for a fixed amount of time. Okay, and as this runs, I'll talk about the meshing of TLM. Now, you may have heard about this, and we can, of course, see a preview of how long this might take down here with an estimation. Of course, this might take a few minutes depending on the length of time we want to simulate. Now, the TLM solver uses an octree meshing. You can view this mesh, and what we'll see is that the initial mesh was about 124,000 cells, so it's relatively small, right? But what happened was, when we started this simulation, there's a process called cell lumping, and you can see what this does is combines areas of dense cells where you don't need them into larger cells, so obviously in all of the surrounding space. So TLM is great when you have fine details to capture, but a relatively large amount of space around a certain structure, basically reducing the overall cell count, in this case by about 70%, you can see. And what that does is obviously minimizes the compute resources, the amount of unknowns, speeds up the simulation. What it also has is something called PVA, or cell warping. So if I zoom into the structure here, we can see that along the curvature of this cylinder, the cells have actually changed shape, right? And this is basically a form of conformal meshing for the TLM octree meshing. In typical hexahedral meshing, you'll have kind of a staircase stepped approximation of a curved structure that's going, on a diagonal through these Cartesian grid of cells. But this is a nice way to have conformal meshing that allows you to have a more accurate representation of that structure, right? So that's running the simulation now. I can, of course, monitor the progress here. And you'll see that when you click on 1D results over here, you'll get a preview of all these results. Now, if you're used to classical time domain simulations in CST with Microwave Studio, you might think about this energy decay, right? And so usually when you're simulating a structure to obtain S parameters, you look at this energy decay as a convergence criteria. In some EMC simulations, we're not really concerned about S parameters or about the energy decay, but rather observing the transient field behavior or observing the transient currents and so forth. So we still do get the energy as an output here, but it's not really indicative of our convergence or what we're after. So of course we can see as this double exponential is ramping up, that energy is ramping up, and that's basically going to stay that way for a long time, as it takes a really long duration for that signal to decay, right? So you have the energy, we have the discrete port current, which we can see basically our excitation is appearing there. Remember that excitation signal is multiplied by that 1 amp that we set in the current port. And we have the probes, of course, as well as the current monitors. So you can visualize all of these results as the simulation is running. So even if this is going to take somewhat of a long time, you can look at the results right away and see if things are making sense, which is really nice. Okay, so looking at these probes, again, I placed a magnetic field probe inside and then 2 of them outside, right? And if I look at the H field results here, I can look at the magnitude of each one. Sorry, this is as a function of frequency. I want to find my probe signals as a function of time. And we can see 0. Well, why do we see 0? That's odd. That's the one inside. Okay, this is 005 outside, 0010, right? So we see less of an amplitude further away from the structure, as we'd expect. Why is this 0, right? This comes down to the materials modeling, and this is a really important point for these transient phenomena where you have lower frequency energy and you want to model this in a field solver. I set this to aluminum, but this is a lossy metal, and what that means is it's a high frequency material approximation. Basically, if the skin depth at the frequencies you're considering is becoming comparable or larger than the metal thickness, then you should no longer use lossy metal because it assumes that the skin depth is much smaller than the thickness and makes an approximation. So basically, it doesn't allow any fields to be penetrated through this material, which is why we see 0 inside. So we'll see that once we modify that to a different material type, we can also then observe the fields inside of this cylinder as well. Because right now it's completely closed and it's modeled as a high frequency material type. Okay, so that's just a lesson with the materials modeling. Again, if I look at the current monitor now, I can also observe the signal, and this is the current that was conducted from that port down the wire through our structure and then exits the model. Okay, so that's all great. Now let's take a look at the fields. We can, of course, look at the surface currents. And you can view these with different scales, which I want to point out over here. Okay, so you have linear, logarithmic. I like to use dB max because we can set a maximum and then look at the amplitudes, a certain level down in terms of decibels. Okay, so we can view, contour plots, and I can animate. I can animate the lightning strike here. So I can also use the arrow keys, which I'm pressing the right and the left arrow keys on my keyboard right now to advance or go back in time, as you can see. So at early time, we have the current coming down the wire, flows through, and then appearing at the exit wire. All right, so that's a transient animation. You can also look at that with these arrows. You can make this structure transparent or not, which might be a helpful hint. And basically, we can see at early time, which I can also change the time here. Maybe at 0, there's nothing. 1 microsecond, 5 microseconds, more. Okay, so that's some basic visualization tips. Looking at the H field, of course, this monitored those fields on the whole entire volume here. Okay. Now, that's nice to look at. It's somewhat insightful, but it's a little hard if you really want to go into the details. So you have something called fields on plane. Okay, I can monitor or observe the fields just on one particular plane here. I can use the scale on the right to change this. So again, we have our current flowing in the positive x direction. Thus, we have from this view a counterclockwise magnetic field. Right. You can also animate this. But the thing I really like to do is use multiple planes, okay, in combination with the ISO lines. So I can activate multiple cutting planes here. We could align these, at whichever location we want to, as you can see like this. So again, we have our high magnetic field on the wire over there. You can see it comes down. And then, of course, same thing at the exit wire. And I can use what's called ISO lines. So let me just position this guy at 0, position another cross-section. And when I use ISO lines, you'll get an output that looks something like this. Okay, and this is pretty nice. You can also choose whether you're looking inside the structure with the cutting plane or not. So you can see I can turn that on and off. And if I restart this animation here, take a look at 1 microsecond, animate the fields in time, and see how that, as that amplitude of the current is rising, you've got higher magnetic field strength and, of course, more flux, which you can observe there. So that's really nice. Okay, so that's pretty basic. But now let's say we want to make some modifications to this. Okay, so in terms of materials, as I talked about, we modeled this as lossy metal. So rather than use lossy metal, I'm going to change this to a normal material type. And basically this means that it's no longer this high frequency approximation. It doesn't assume that this is a good or a really good conductor. But at normal, I have an epsilon, I have a mu, and I have a sigma conductivity here, and I can apply this. Now, this ends up being a material inside of the stack-up of what we call thin panel. We want to take into account the field penetration and model the skin depth of this material, but again, in this case, I had a 0 thickness, which of course maybe you'd put in the actual thickness, but that might be very, very thin. And if it's very, very thin and you have to resolve that with many cells across that thickness, that's going to, minimize the time step for the simulation. It's going to increase the simulation runtime, increase the overall cell count, the resources needed. So thin panel material allows us to still model it as a 0 thickness sheet, but to model analytically, internally to the code, the accurate skin depth and penetration behavior of those fields and currents. So a new material I would create is called thin panel. And with this thin panel material, which I'll call thin aluminum, I can define the stack up. And again, this can be multiple layers. It can be different materials stacked up with different thicknesses and different rotation angles. And this is especially important when we talk about carbon fiber composites modeling, as we'll see on this last model coming up. So I can specify the aluminum. Say I use a thickness of 1 millimeter, and then I can apply this. Now again, once I've set up this new material, I want to change my cylinder to that, and that's just a simple drag and drop. Thin aluminum, drop it onto the cylinder, and there we have it. So I didn't change the color, so it's blue now, but you could if you want to. All right, so this is just some tips and tricks again. I'm trying to give you guys ways to improve your efficiency with the tool, basically. Now, what I could do is also then create a more complex geometry here. Okay, I could move my working coordinate system here, maybe to this face with a pick and using W. And I could create, let's see, I transform this here. I can now create maybe a cylinder or an elliptical cylinder, let's say. And this is going to be oriented along U with a certain radius, perhaps 0.5 and 0.3, and maybe -4 to 4, something like this, maybe in the shape of a window, yeah, along this fuselage. So if I make this vacuum and ensure that this is going to cut through that, that's going to prompt me now, what do you want to do? You have a shape intersection. I can say insert the highlighted shape. Okay, now my cylinder has some cutouts, and I can make use of a transform function here in modeling. Transform, translate, and I can make multiple copies of these at a certain translation vector. So maybe, 1 meter away, and I make a copy, and I make 20 of these, right? Something like that. Maybe 40, 45, something. Can unite those. And again, now I'm going to have an intersection warning. I insert the shapes. And now this is starting to look like an aircraft fuselage. Right, so I just want to show you can really create within the modeler some representative geometries, even if you don't have the complex CAD data yet, to do some kind of simple studies like this. Okay. Now, I'm running a little short on time, so I'm going to switch over to this window. And I had already done this with the previous example model, as you can see. I have my current monitor. I have my field probes inside here. And I've actually set this one up to be thin aluminum, as we saw with the thin panel material. And I ran this one here. So now we can see we're going to have certainly a non-zero magnetic field internally, right? And that's at this 0, 0, 0. You can also see, you might expect the magnetic field on the side over here, since you have, the current flowing along the x direction. You expect this magnetic field to be primarily dominant in the y direction, as it's encircling around that to the side here. And you can see that because you have different components, both the x, the y, and the z, and you can see how much larger the amplitude of the y component of that magnetic field is, right? So that's something else. And of course, now that I've got these holes penetrating through here, it's a lot more interesting when we look at the magnetic field, in this case, as a function of time. I can plot this as isolines. And if I activate my multiple cutting planes here, okay, we can set these up as x, y, and z. And we can see that magnetic field penetrating through all these little mock-up windows here, right? So that's pretty nice. So again, that's a very simple model, but you can, of course, imagine building this up to the complexity of a real aircraft model. So I'm going to switch to my other remote desktop here. And here you can see this mock-up 787 model, as we were showing on the earlier slides. Now, this one's been set up pretty much the same exact way in terms of, you know, the lightning channel. You can see here the port at the end there, and the exit wire. We've got some current monitors placed around the front fuselage and the back. And these green lines you can see, these are actually seam models, or basically these compact models. I'll show you a reference to Yushi's webinar, which was just several weeks ago, and he really went into depth about how to define these compact models. So if you're interested in that, you can check that Getting Ahead with webinar out as well. But basically, along all these doors, we can define the seams so that we can model the leakage of the fields internal to the aircraft through those seams. Compact models like seams, slots, wires, thin panel is also one. And in this case, the thin panel has been defined, you can see, called CFC laminate with a certain thickness. If I go to my materials here, I can see that I have carbon fiber as an anisotropic material with a conductivity differing in X, Y, and Z directions. And then my thin panel called CFC laminate is actually a stack-up of this carbon fiber material with a thickness parameterized as pi d and with different rotation angles. And we can also then add a layer of copper mesh. So of course these composites make the aircraft so much more susceptible, but we can include layers of wire mesh to help with the lightning protection. So this can also be modeled. Right. Now, again, we have basically similar outputs. We have the current monitors and the field monitors. So you can take a look at all of those. But the other point is this has a cable modeled. So you can see the cross-section here. Right now, we're actually within Cable Studio, which is embedded in the CST Studio Suite. So Cable Studio allows us to go ahead and model complex cable geometries inside of larger electronic systems, like an aircraft. Okay. Basically, we have a way to transition models directly to that within the interface. So here was my test vehicle from before with the windows. Let's say I wanted to change this to a Cable Studio model. It's relatively easy. I go here to Problem Type on my home ribbon. I select Cable. And now I'll be inside of the Cable Studio environment, which basically gives me this additional cables ribbon, as well as the cable navigation tree where I define my bundles and a cross-section view and so forth. Cable Studio also couples to the schematic. Basically, we have a cable bundle, and we're going to spatially model that within the 3D solver, but then we have a schematic which defines sources and terminations for that cable. Okay. So we can see here this was actually just a cable inside of the library, which is a USB 3 cable. But we have a shielded differential pair, an unshielded twisted pair, the overbraid, and so forth. And we can look at, for instance, the overbraid current that's resulting from these indirect effects of that lightning strike. So you can see that's ramping up here to almost 1,000 amps using that same 200 kiloamp waveform. We can also take a look at this as a function of frequency and look at the pin voltages of those individual wires as well. So just to come back to the slides and to conclude here, 1 second. So lightning strike simulation, I wanted to give you an overview of this with a focus on this return stroke analysis and indirect effects. Of course, lightning is inherently a multi-physics and multi-scale phenomena and problem, so there's lots to consider. It's very challenging from simulation point of view if you want to think about all of these different effects. But there's lots of R&D ongoing in this, and especially to look at more multi-physics capabilities with our software. EMC and E3 simulation itself is also inherently complex. There's always lots of variables. There's always lots of questions of what do I include, what should I neglect, right? And I love this quote from Albert Einstein, which says, everything should be made as simple as possible, but not simpler. And this really, brings the point home, especially with EMC simulation. You've got to consider the right variables, but you don't need to include every single detail, and you certainly don't need to try to mimic an exact test setup for your EMC standard. But you can still use modeling in a way that helps you learn about the phenomena and also helps you design early on in a better way. And of course, we're here to help from technical support, so please don't hesitate to contact us there. Lightning really requires a complete technology approach, including statics, quasi-statics, thermal structural, full wave, and all of that is contained within CST Studio Suite and Simulia. So we've really got a nice solution for lightning strike simulation. Again, simulations for this aren't just aircraft exclusive. I know I showed aircrafts and kind of aerospace defense applications today, but here you can see a cell tower, a wind turbine, a spacecraft launch setup. So you can really use this for many types of applications, and it's kind of a cross-industry application, of course, as well. All right. So just to give you further info really quick before the questions, here we have on our website, you can go to the Events and eSeminars archive, and I just wanted to point out these past 2 webinars because they'll go into more detail about the other aspects, so from David on E3 simulation as a whole, but also from Yushi just several weeks ago with these compact models, because if you really want to see how to define those seams, how do we define event, what are the specifics and the the gotchas with the modeling of that, that's a very good resource for you as well. We also have a nice new shielded cable modeling app note, so contact your support if you want to take a look at this in more detail. How do we approach modeling shielded cables, not only with Cable Studio, but with the TLM solver? And on the support website, or on the CST website, you can go here to support, of course, to get in touch with us if you have further questions. I also just wanted to take the chance really quick to say come see us at the following events in 2018. So with that, I'll just, at the very bottom, just want to point out, stay tuned for our E3 EMC Simulation Symposium, which will be later this year. This is a follow-on to our E3 workshop last year, so if you're interested in contributing or participating in this, please contact me. And thank you for the time and attention, and I'll answer any questions you guys have.